All right, so just imagine pleasant music, and I say, I am Alistair Cookie. Welcome to Monster Peace Theater. Let's talk about paired samples t-tests. One of my favorite things to talk about. Wrote a song about it once. I called it Dependent Means. It was about one mean that was in love with another mean, and they were dependent. Get it? They were dependent. Okay. Let's get to the lecture part. Yeah, you're going to see my really embarrassing me Googling how to do this crap. So let's get started with the lecture here. We've talked about single sample means. We've talked about our single sample Z and t-test for the difference between one sample mean and some hypothesized null hypothesis mean. And then we've looked in the last lecture at differences between two means that are drawn from two samples that we think are independent, two independent samples. And now let's talk about paired data. Two means from paired samples data, so a z-test or a t-test, sometimes called a repeated measures z-test or a repeated measures t-test, sometimes called a t-test for dependent samples, sometimes called a test of differences between means for the same sample measured twice, sometimes called a test of difference for two means. People can't agree on what this thing is. The most common thing is a dependent samples or paired samples t-test, but these are things I've seen in previous textbooks I've used. They get a little crazy. So your data structure is el numero uno important. You don't use this unless your data is set up in a paired manner and your research hypothesis requires you to use this structure to deal with your data. So you have to have one group of subjects, two measurements per subject, therefore having two groups of observations. So this is the setup, as we saw in a previous lecture on just t-tests or two sample mean tests in general. So this is your setup. You have to have one group of participants, and each participant provided you with two observations. So here we have this situation. You've got, I was trying to think of how I could set up my little graphic thing to make sense with this, because it's not two groups of people anymore. It's one group of people, and the observations are, anyway, let's see if this works. So let's imagine that you've got this group of people, and they're in one situation or one condition. Is this one way that they're thinking of something, or one mindset, or one kind of score from them? So you turn on this condition. Let's say the condition is you shine a blue light on them, and your dependent variable is, I don't know, how much nervousness they have. So you shine the blue light on them and you measure their nervousness. And so you get an observation from each person. And so you get this data set. There's not nearly enough people there to account for all the blocks. There's like 100 blocks and only 8 people, but still. So when that's happening, you're basically saying, I'm getting data from some distribution, some population. And if your alternative hypothesis is what you're thinking of at the moment, then you're thinking that's different from the next situation. The null hypothesis says it's the same as the next situation, but I'm getting data from some population. Now, the population isn't a group of people. The population is a group of observations that might happen under certain conditions. So in this case, it's the population of all possible responses that, like, all possible students or something might have if they were exposed to blue light. So let's give them a different influence, the red light influence. Is that reddish, purplish? I hope. And that gives us a different set of data. Same people, different set of data. And what we're saying there is that those observations came from the distribution of all possible responses of students to having a red light shined in their face while they were giving anxiety ratings, which sounds pretty nerve-wracking to me, now that I made that up. So are you understanding the setup here? It's the same group of people, but because you treat them one way, or because you're asking them one type of questions, then their data are conceptualized as coming from a certain population. You treat them a different way, or you ask them different questions, and their data come from a different population. Now, you don't know if that population is different from the first one or not. That's the question. That's our big question here. So you take a sample mean from each of those sets of observations. You look at the difference between the means. The alternative hypothesis, of course, says that these two groups of observations came from two separate populations. In other words, that there are actually two separate processes or separate situations responsible for the way people responded. That the way they responded in dependent variable version 1, the way they responded in group 1 at test time 1 was due to something fundamentally different from the way they responded at test time 2. So the blue scores are due to a different process from the red scores. So the blue scores are because they were having a different reaction to that blue light than they were to the red light. That's the alternative hypothesis, two separate populations. Pretty similar to the independent samples case, but you have to think about it differently to make it work. Now, unfortunately, there is always this null hypothesis, and the null hypothesis says there's only one distribution. There is no, so yeah, sure, you've shown different lights on them, a red and a blue one, but that didn't cause any different reaction. Mentally, nothing changed. They were still mentally and psychologically in the same space they were at before. Their anxiety did not raise or lower at all due to the light change. If it looks like it did, that was just random sampling. You caught them at a bad moment, used a weird kind of light or something like that. So the null hypothesis says, yeah, you got all this data, but you got it all from one big fat distribution, the distribution of how people respond to lights in general. There's no special red light and blue light response thing. The alternative hypothesis says there is, but the null hypothesis says there's no difference. There's only a light responding thing. Now, this would have to be formulated differently for every single hypothesis and every single research situation. And doing that is actually pretty important, but it does get a little fussy sometimes. So if the null hypothesis is true, then of course, we construct our sampling distribution of means. And if the null hypothesis is true, it doesn't matter whether mean 1 and mean 2 in the population are positive 1 million or negative 1 billion or positive 0.3 or negative 2.98. If they're the same as each other, then the mean of all possible differences between means is 0. And we're going to do a little judo trick on here. To start calling that, instead of the difference between means, we're going to call it the mean of the differences, which is an important little flip that we have to do for this. So the shape of that, if we're using z-test, as you know we're not going to, is normal. When we switch to t-test, it will be t-shaped. The standard deviation is the standard error of the differences between means. So we have to set up our data in paired ways. We have to conceptualize it slightly more complicated than the independent samples t-test, but the calculation is much easier. The calculation is essentially the same as a single sample t-test calculation. So you just use, the key is that we take, since there's each person gave us a score 1 and a score 2, we just take score 1 minus score 2 for each person. We use the pairing and we create different scores, 1 minus 2. So we end up with one set of scores instead of 2. So we don't have to deal with two means. We just look at one mean, the mean of the differences. So we're not going to be looking at the differences between the means. We're going to be looking at the mean of the different scores. And mathematically, that's the same thing. The mean of the differences is the same as the difference between the means in this situation. So calculating our observed statistic is the same as for anything else. We have a point estimate. In this case, the difference in the means or the mean of the differences from our sample is the point estimate of what the mean of the differences or the difference in means is in the population. We have a null hypothesis value, which is 0, because the null hypothesis says there is no difference in the population distributions there. And we have a standard error of the differences, which is much easier than in the independent samples case, which is saying something because that's already pretty easy. So this is even easier. So this is almost always 0, and we've got a standard error here. So we set it up the same way. We have a z distribution, or as we'll see in a minute, a t distribution. Now, note down here, this is not x bar 1 minus x bar 2. This is d bar. So d is what we're going to use sometimes to talk about a difference between two independent or between two paired observations. The mean of all the differences is d bar, and all of those means together form a distribution of all possible things. So this might as well just say x bar. It's just a distribution of means. It's the sampling distribution of means, but it's the sampling distribution of means where each mean was calculated from different scores between two samples. So it really does encode all the information about the two samples and the two means, but it does so in a kind of a sneaky little way. But same issue. You mark off the top, 0.025 and the lower 0.025 if you want to have alpha is 0.05 two-tailed. And then you calculate a z-score from the actual mean of differences or difference mean that you've got from your sample. And if it falls in the rejection region, you reject the null hypothesis. Hooray, you go home, you get published. As soon as you finally write your paper, which takes a long time. So the standard error of the differences, you just have to remember that little judo flip. You were dealing with differences, not with individual scores. Now you cannot do this with independent samples. It doesn't make any sense. Like, who would you subtract from who? You got Fred and Marcia and John in one group, and Raul and Femti and I don't know, Janiqua in the other group. And who do you subtract from who in one group versus the other? It's crazy. There's no way to know how to do that. So don't ever try and do different scores with independent samples. You can only do this with paired samples. So if you've got Fred and John and Raul and Femti and Janiqua all in the same group, and they gave you a score 1 and a score 2, well, it's Fred's score 1 minus Fred's score 2, and Janiqua's score 1 versus Janiqua's score 2, etc. That makes sense. So that's what you do. You, for each case, which might be a person or it might not be a person, for each case, and always going in the same direction, like 1 to 2 or 2 to 1, just be really consistent, you subtract that person's, one of that person's scores from the other score. And then you just have a column of one row of numbers. And then you take the mean of that numbers, and that's what we sometimes call D bar, the mean of the differences. The standard error of the differences is just the same thing as the standard error of raw scores. It's just the standard deviation, except instead of the standard deviation of the raw scores, it's the standard deviation of the different scores divided by the square root of n. And n is the number of differences, or the number of cases, not the number of original observations, which would be twice as many. Now, as a note, in some versions of the OpenIntro 2nd edition textbook, they forgot the radical sign on page 214 in an equation near the bottom of the page. If you do the math, it won't work out without the radical sign, but just be careful. You've got to put that in there. So paired sample z-test. N is the number of pairs of observations. Mu0 disappears because it's 0. So we've got our point estimate, which is our mean of differences. And then we want to see how different that is from the null hypothesis expected difference, which is the mean of differences in the population, which would be 0. And we divide that by the standard error of these differences, of these mean difference scores here. So that becomes 0, so the formula is really similar. You just take your mean difference divided by the standard error. There you go. Now, just a reminder of that. Okay. So the standard error of the difference is just the standard deviation of the difference scores. So just like a single sample test, but once you create those different scores, then you pretty much just pretend like they're a single sample of data, and then you just proceed from there. So when the standard deviation is not known, which is all the time, then we do a t-test, which of course looks just like a z-test. The distribution is so similar to the normal distribution that most people can't tell most t distributions from z distributions with the naked eye. But you have to use them, or else your numbers turn out wrong, and you're overestimating some things and underestimating some things. And basically, you make science cry if you don't use this in the right circumstances. So, but it looks and acts just like a normal distribution. The numbers are different, but it behaves the same way. We use it the same way. So the mean of all the differences is, of course, 0. This is the distribution of all possible difference scores. So it's the sampling distribution of differences between means, or mean differences, same thing. And we calculated an observed t-value. After we look up our critical t-value, we calculate the observed one, we compare it to the critical value. Was it in the rejection region? Hooray, we reject the null hypothesis, and we go home happy, and we get to pay rent yet another month. So starting from different scores, I don't know why that was in there twice. Oh, it's because we're talking about t now. Let me go back here. It's the same thing, except instead of z here, we say t. It was so similar, it fooled me. It's the same thing. But down here, it's not going to be square root of n. It's going to be square root of n minus 1. This is the degrees of freedom for this test. It shows up here, and it shows up when you have to look up the t critical value. So the number of pairs, or number of cases, minus 1. So that's your formula to calculate your observed t-value. So an individual difference score, etc. So nobody actually provided you with the population standard deviation of differences, and you're never going to get that. So we calculate the sample standard deviation of the different scores. And you do that just like you do for the standard deviation. So here's the formula for standard deviation, right? The sum of all the deviations of each raw score from its mean squared. You add all those things up. The squared deviations, you sum them up, divide by n, take the square root, then you've got your standard deviation, right? Well, we do the same thing, it's just that we do it with different scores. It's the same thing. It's just a column of numbers, the same as the x's were a column of numbers. The process is identical. The hard part is remembering that it's different because it feels exactly the same. So there you go. The standard error of the difference for a t-test for paired samples data is the standard deviation of the difference scores divided by the square root of n minus 1. N is the number of pairs. So all these questions, what's the sample point estimate, the difference between two sample means, or the mean of sample differences? The sample point estimate is the difference between the two means, or the mean of the different scores. What's the sampling distribution? All possible different scores, difference means, or all possible means of differences. It's equivalent, whichever one you want to say. What's the mean of that distribution? 0. It's always 0 in two sample situations. And what's the standard error? Easy. Standard deviation of the differences divided by the square root of n minus 1. There you go. So step by step, same as with everything else. You're going to draw and label your graph, your diagram. You're going to find your critical t-value, which you'll need the degrees of freedom for, and your alpha level for. You're going to calculate your t-observed, which is super easy. You're going to compare the two, probably plot them both on your diagram to make sure you make the right decision. Make your decision about the null hypothesis, state your conclusion, and go home. So what's the sampling distribution? It's the distribution of the differences between means, or in this case, the distribution of the mean of paired differences. So all the means of paired differences, or all the differences between paired means, either way works. They're the same thing. So if you set up your data correctly and you apply the formula, this is all you do. Super, super easy. This is calculating t-observed. This is the hard part. Sometimes people will say, here's how you do a t-test. And they're right. This is the mechanics of it. But that doesn't mean you'll get the question right, because you need to identify the situation where you should use this t-test and be able to interpret its outcome. The mechanics are really easy. So then you just do all the other stuff so it makes sense. That was easy to say, hard to do. So I'm going to repurpose the same scores I had before, but I'm going to make them different situation. I'm going to pretend like there's something different because, you know, I didn't make up any new scores for this lecture. Sorry. I should make up new numbers sometimes. But if you want to compare the results here to the results we got before, you might be interested to find that they are not the same. So let's say there's a bunch of people, 10 people, and they're all recruited for a study because they all have low social confidence. And they're given a social confidence questionnaire after they get done with an intervention. Now, we actually intervene with each person twice. One time, we give them cognitive therapy for a few sessions. And another time, we just give them placebo therapy. Now, sometimes placebo therapy is talking to a friend or just chit-chatting or doing a video journal or something, or sometimes even just sitting in a room for an hour and not doing anything, like reading a book or something. So we probably, to prevent any order effects, like we don't want to make it so that all the people who got cognitive therapy went first, we probably randomly alter who got which one first. So we do that. We take care of all that. That's research design, though. That's not really statistics. So we counterbalance the order like that, and everybody gets both of these things. Sometimes they get cognitive therapy and then wait a few weeks and then they get placebo therapy. Sometimes they get placebo and wait a few weeks and get cognitive therapy. So we're not going to look at that. We're just going to assume it was done well. So everybody has 2 scores now. They have a score for their cognitive therapy and a score for placebo. The scores are their social confidence scores, so higher is better. And so it looks like there's more double-digit stuff over here in cognitive therapy, and it's the same numbers as before. So we're going to ask, did cognitive therapy increase the test scores relative to the placebo? Now, there are 3 things different from the previous example with independent samples t-test where I used the same data. I even use the same names. I'm pretty lame that way. The 3 things that are different is, number 1, this is paired data. Number 2, alpha is 0.01, and it was 0.05 before. That's important to note. And number 3, this says increase. So this is going to be a one-tailed test. So if this mean had ended up higher than this mean, we wouldn't even do any statistics. We'd say, we said increase. It didn't increase. We're done. Null hypothesis accepted. Alternative hypothesis not accepted. We're going home. You failed. So with a one-tailed test or a directional test, you run that risk. If the means are in the wrong order, if the wrong one is high and the other one is low from what you predicted, you don't even have to do any tests. You're just done. because you know the test is not going to work. It's not going to show that things worked out for you. So remember that the mean of the differences is the same as the difference of the means. So we can look at the means here. Oh wait, maybe it's not the same data. You're right, it's not the same data. We can look at the means here, 9.5 over here, 7.4 here, and the standard deviation 1.5 or 1.9. We don't really use those. If this was an independent samples condition and there were 20 people, maybe we would, but here we don't. Instead, we calculate differences. 9 minus 6, Fred's difference score between cognitive therapy and placebo is 3. You can think of this as the amount that cognitive therapy social confidence was greater than placebo was 3. Alice, it was 0 greater. Jenny was 2 greater. When you go down here to Sayadit, you have, it was actually 3 worse. She got worse. Placebo was better. Well, she didn't get worse, but placebo did better than cognitive therapy. So cognitive therapy was -3 better than placebo, right? So it was not better at all. So anyway, you just do this. And then you pretty much forget about the original data. You calculate mean of the differences and the standard deviation. If you punch these things into your calculator and do just a standard deviation formula on these, you will get this. So mean and standard deviation. Something to note is that the mean of these differences is the same as the difference between the means. 9.5 minus 7.4 is 2.1. And that's also the mean of 3, 0, 2, 1, 1. That's the mean. But that does not work for standard deviations. It's sort of like an average of the standard deviations, although in some cases it won't be a straight ahead average. In this case, it's not. It's actually bigger. So notice how the variation of differences can be bigger than the variation of either of these scores. So you can't subtract, you can't add. You just have to go back to these numbers and actually calculate the standard deviation. There's no shortcuts for that. There are certain situations where there would be shortcuts, but it's not worth trying to remember what they would be. You just have to calculate everything. So the null hypothesis is that there is no difference in outcome between cognitive therapy and placebo. The alternative is that cognitive therapy results in higher outcome scores than placebo. The null hypothesis is mu for cognitive therapy minus mu placebo 0. Alternative, cognitive therapy minus placebo is greater than 0. Notice again, these are the population values. You never put sample values. The hypotheses are about what's going on in the population. We use the sample to test that, but the sample doesn't go in the hypotheses. Or you can write it this way. So here's my diagram. I've only got one tail. I said this is a t-distribution with 9 degrees of freedom. So that's the shape of this thing, and the areas under it are defined by that shape. You can't find accurate areas or p-values or alpha values or anything unless you find the right t-distribution. There's actually lots of t-distributions, and we need the one that is 9 degrees of freedom. And so we're going to find a t-critical value. I'm just going to draw a line here because I know it's going to be on the right. As long as I said everything is measured as cognitive therapy minus placebo. Cognitive therapy first, placebo second. If that's the case, then if cognitive therapy ends up having a higher score, which is what I hypothesize, and placebo lower, then the mean for cognitive therapy minus the mean for placebo will be a positive number. Therefore, we put our tail on the positive side of this distribution. The null hypothesis says that in the population, the difference is 0 between all sample means on average. So our sample mean, if it shows an effect, is going to be greater than 0. Alpha is 0.01. We put the entire 1% in this one tail. And we can tell it's going to be here because this is actually labeled. But anyway, we don't have to know the value to draw t-critical over here. It doesn't have to be to scale. To look up what t-critical is, we need to know alpha, 0.01, the number of tails, 1 tail. So that's going to be the same column as 0.02 and 2 tails. We're going to have 9 degrees of freedom, which is the same as the other one we did because we used the same data. And it's n is the number of pairs, not the number of individuals. So in this case, t-critical is 2.82. It would have been the same as before, but we're using a different alpha level. So if you want 0.05 in one, or 0.01 in one tail, it's the same as 0.02 in both tails. So let's go back here and see why that, well, let's go forward and see why that works. So right here, if you have 2.82, it cuts off 0.01 in this tail. If you also had 2.82 down here, it would cut off another 0.01, and altogether your alpha would be 0.02. That's why you look things up in this column. It says 0.01 in one tail or 0.02 in 2 tails. It gives you the same t-values. So if you have a 2-tailed test, you use this. If a 1-tailed test, you use this. But you never have 2-tailed with alpha as 0.02. That's a little weird. All right. So this is our setup. Our critical t-value is 2.82, and we're going to see where our sample mean falls. It's going to be to the right of 0 because we already saw that cognitive therapy had a higher mean value than placebo. So we know we're on the right side of the distribution just from looking at the descriptive statistics. So we calculate t observed. The mean difference divided by this. So these are the numbers we punch in. This was the mean difference. This was the standard deviation of all the differences. Square root of 9, 10 minus 1. And this gives us 2.46. That's looking pretty good. Not good enough. Once again, we fail. I think I set it up to fail on purpose. I'm self-defeating. Now the p is 0.018. So alpha is 0.01. P is greater than that. Alpha is almost 0.02, right? It's 0.08 because P is the area from the purple line, from the observed line, all the way out. We don't have to do something on the left-hand side because this is a one-tail test. Our entire alpha and our entire P are in one tail. So our p-value is over here. Now what would happen if we had a one-tailed hypothesis over here and we said cognitive therapy is going to be greater than placebo? And in fact, something weird happened and we were so wrong, and placebo produced higher social confidence scores than cognitive therapy. Well then, cognitive therapy minus placebo, small minus large, we would have gotten a negative value for cognitive therapy, or for the t-value of the difference between the two, between cognitive therapy and placebo, CT minus placebo. And our p-value would have been like 0.9 something, or anyway, it would have been greater than 0.5, because the p-value and a directional test only goes in one direction. And if your observed statistic falls over here, well, sorry, you're just screwed. You just have a pathetic and terrible and horrible, gigantic p-value. But in this case, the p-value was close, but no cigar. If we had had an alpha level of 0.05, which is more common, we would have rejected the null hypothesis. But we set our alpha at 0.01 for some reason, known only to us, and therefore we do not reject the null hypothesis. Now, it is totally against the rules to go back and say, wait. Now that I saw the results, let's change it to 0.05. No, against the rules. Okay. All right, so our decision is that we failed to reject the null hypothesis because we did not have a big enough difference to satisfy our hypothesis test at the alpha level we chose, which is 0.01. Kind of a harsh alpha level, but we chose it. Our conclusion is cognitive therapy does not result, or you could say the evidence does not support the contention that cognitive therapy does this. People phrase this different ways. This is a little sloppy. Cognitive therapy does not result in statistically significantly higher social confidence scores after therapy compared to placebo. Now, with this presentation of that junk in the parentheses, I'm going to explain it. Almost always when you're writing a paper for publication, for a term paper, something like that, and you have to do an analysis, like say for your research methods class, when you report the results of a statistical test, so a t-test for instance, you have a conclusion statement, and then before that sentence is over, before the period, in parentheses, you put the technical information, a brief summary of the most critical technical information people want to see. Not everything, but there are only certain things we put in there. This is what we put in there. We put the statistic type, so a T. Sometimes the statistics require some modification, usually degrees of freedom. So we're going to put the degrees of freedom. Sometimes that just goes in some other parentheses when people can't figure out how to do subscripts. We put the value of the observed statistic. So 2.46 was T observed. P crap. Well, I fixed that now. P is greater than 0.01. So magically switch that right before your eyes. Sometimes people will say one-tailed or two-tailed in those parentheses as well, but always this stuff. And the alpha level goes there. So alpha is not the actual p-value. Sometimes people put p equals, 0.018 or whatever it is, but that's sometimes seen as a bit lazy, like you just dumped what came out of your computer because it would have said p equals 0.018. You need to be the researcher and say, this is why I made my decision. I had an alpha level and I compared, and p was not less than the alpha level, therefore. So don't be lazy. So finishing this up, let's just remind ourselves of all the tests that are out there. There are 3 that we're going to be concerned with. We're never going to use this, really. We'll use the T observed. We'll use the t-tests. The single sample t-test, the paired samples t-test, and the independent samples, or independent groups t-test. And that is all.